at Tn, we have the transmission finished. Since the transmission will be finished, the state of the Markov chain with the probability 1 will go to state I, which is the idle state. So if we summarize, we have three states. One is the transmitting state, which has actually multiple similar stages or similar states, T1, T2 up to Tn. And we have a collided state or collision state where actually two or more stations transmit simultaneously, and within a time period tau c, tau sub c, all of them actually identified a collision has occurred, and immediately they cease their stop their transmission and come back to state I. On the other hand, when the Markov chain goes to state T sub 1, T1 from I, since a single station is transmitting, with probability 1, it moves on to T2, T3, T3, T4, up to Tn, and at Tn, with probability 1, it goes to I. Now, what is the probability that the channel will remain idle in a time period tau c? We assume that there are n identical stations. All of the station transmits with a probability. A is the probability of Tx by any station in a time period, in a time slot, tau c. And whether it's a retransmitted frame or it's a fresh frame, the probability remains same as you already assumed. So the probability that k stations are simultaneously transmitting is binomially distributed with probability n choose k, a to the power k, 1 minus a to the power n minus k. So 0 station is transmitting when k is equal to 0 will be n choose 0 is equal to 1. A to the power 0 will be 1, so will be 1 minus a to the power n. So this says none of the n station is transmitting. Probability A is the probability that a single station is transmitting. 1 minus A is the probability that any station is not transmitting. 1 minus A to n is the probability that none of the n stations actually is transmitting. Second probability that we need to find is U sub 1. U sub 1 is the probability that a single station is transmitting. We can get it from 1. Here, n choose 1 is n. A to the power 1 equal to A, and 1 minus a to the power n minus 1. So this is the probability that a single station is transmitting. And this probability is that two or more stations are transmitting, which can be calculated by using this formula, which will be k equal to 2 to n u sub k. You will get the same value, or you can just calculate in this way. Either way, we can get the probability that two or more stations are transmitting. And are leading to a collision. The collision will occur here and then the. Now, two questions are here. One is the last year question. Another one is, instead of CSMS-CD, if the protocol would be CSMS-CA. So how the transition probability state transition graph will be actually changing. If it is CSMS-CA, that means collision avoidance is the mechanism for wireless network, then how the state transition graph will be changing. And second one actually is, if we assume an artificial CSMS-ready protocol where a station after successfully transmitting a frame, actually decide what if it has multiple frames, then it decides whether it will continue transmission of a second frame or it will go back to idle state. In the first case, with the probability C, it continues the transmission of the second frame. So from Tn, once again, it goes to T1, T2 up to Tn again. Then it go with probability 1, it goes to idle state. And this occurs with the probability actually C. Here Tn to T1 occurs with the probability C, and Tn to idle occurs with the probability 1 minus C. So this is the case. And in case of CSMA-CA, so I actually asked the question, what will happen if the protocol would be CSMA-CA? Anybody has any idea? Anyone is hearing?
Yes, sir.
Anyone is listening to me?
Yes, sir.
Yes, yes, sir.
Is the question clear?
Yes, sir.
The question is, in a state of CSMA-CD, if the protocol would be CSMA-CA, then whether we will have the same state transition diagram or we needed separate. If we need a separate diagram or we need some modification, so what those modifications should be. Okay, let me make it further clear. In case of a CSMA-CA, we cannot detect collision. If a station starts the transmission, then it continues. And I guess I explained in the last class what happens. In wired LAN, we have actually two separate cables. One for uplink, that means a dedicated pair of cable or cable, a dedicated cable set of cable is used or pair of cable is used to forward the packet from the center to all other station or the switch. And another dedicated cable is used to receive the packet from the switch to the sender. So while sending the packet, the sender can also receive the packet. In case of the wireless network, it uses a transmitter, which is consisting of two parts. One is the transmitting part, another one is receiving part. But the problem is these are devices and the transceiver can be tuned either to transmitting state or to receiving state. That means when a station is transmitting, it cannot receive. When it is receiving, it cannot transmit. So in that case, when a station starts the transmission, actually, even though a collision occurs, it cannot detect in case of wireless network, where it can detect in case of wired network. Since it cannot detect, it keeps transmitting. And we have up to Tn. After Tn, actually, the station goes back to idle state. So we will see it later. Now, for now, our next task is to write down the probability transition matrix. In case of the probability transition matrix, actually, the number of states will depend on the value of n. For simplicity, we'll assume the value of n equal to 3 or 2, so that the number of states will be less. And if we have n equal to 3, sorry, if we have n equal to 3, then the transition probability matrix will be this one. As I mentioned in the last two classes, that we will not using this style of writing the transition probability matrix. Rather, we will be using the original one that we have been using for this course. And this one actually is the transpose of the matrix that we have. Anyway, so if we just consider when the channel is in idle state, what is the probability it will remain idle in the next state? That occurs with a probability U0. And so we have an entry U0. Now, so we have this one is idle state. I, this is T1, this is T2, this is T3, and if T1, T2, T3, T1, T2, T3, and then you cannot have a T4, right? This is idle, then T1, T2, T3. The current state is T3, then the next will be, actually, we can consider this is T3, and this one is a collision state, TC. So we can even ignore this line. Now, for here, it is n is equal to 4, I guess. So let us see. Why not? Why 2, why 3? Okay. And then if the current state is idle, then the next state will be idle with probability U0. If the current state is idle, next state will be T1 with probability U1. So we have U1 here. If the next current state is idle, next state will be a collision state with probability 1 minus U0 minus U1, this one. And we have actually two other states. You can consider this is idle. This is T1, this is T2, this is T3, and this is TC, a collision state. Now, if the current state is the transmission one, this one, then what will be the next state? Next state will be T2 with probability 1. So if the current state is T1, next state will be T2 with probability 1. If the current state is T2, next state will be T3 with probability 1. If the current state is T3, next state will be the idle state. So after transmission, it will goes back to the idle state with probability 1. So we will have 1 here. And if the current state is a collision state, so after the time period tau C, it will go back to the idle state with probability 1. So this is the Markov chain for actually 5 states where we have the idle state SI, transmission state T1, transmission state T2, transmission state T3, and the collision state TC. And these three actually are the frame transmission times where these are the product of the collision, multiple of collision detection time. Here we assume that a successful frame transmission time is the 3 times of the, for simplicity. Otherwise, our Markov chain will be very big. Now, once we have the transition probability matrix, then if we write down the probability, if we consider that these are the steady state probabilities following the text, or we can consider the probabilities are. For this one, it is idle state pi naught. Transmission states are pi 1, pi 2, and pi 3. And the collision state is pi c. Then, as you already know, the steady state solution of the Markov chain will be pi naught. Actually, can be defined by solving a system of linear equation. The system of linear equations will have, since there are 5 states, we'll have 6 equations. The first equation will be for pi naught, and it will be found from the first column. How? Pi naught equal to U naught times pi naught. Did I write this way? Pi naught times U naught. So pi naught times U naught, first quantity. Then we'll have this one. This will be plus pi 3 times U naught plus, my mistake. This will be pi 3 times 1 plus pi c times 1. This is the first equation. For the second equation, we'll have pi 1. We'll get from this column, it will be pi 1 equal to pi naught times u1. All the elements are 0, so we stop here. Pi 2 will be here. So pi 2 will be this one. This is, what is pi 2? This one. Pi 2 will be this column, and this column we will find it. This one will be pi 1 equal to pi 1. So we can write it is pi naught equal to u1. Pi 3 will be from this column, it will be equal to pi 2 and will be equal to pi naught times u1. And finally, we'll have the equation for pi c will be from this equation, this column, and will be pi naught into 1 minus u naught minus u1. So from each of the columns, we will have one equation. And finally, we'll have equation which is pi naught plus pi 1 plus pi 2 plus pi 3 plus pi c equal to 1. Fortunately, for all of the equations, pi naught, pi 1, pi 2, pi 3, and pi c, we have represented the equation in terms of pi naught. So if we put the values of pi 1, pi 2, pi 3, and pi c here in this equation, then actually we will get the value of pi naught, which is from here. We have this equation, the normalization equations. We know pi 1, pi 2, pi 3 are equal to pi naught u1 and pi c equal to this one. So once we have this one, what we can do, we can put the values of pi 1, pi 2, pi 3 from here, and all of these will be replaced by pi naught u1, and pi c will be replaced by pi naught times this one. Solving this equation will result in pi naught equal to 2 plus 2 u1, 1 over 2 plus 2 u1 minus u naught. So the similar result is found in the text. They did not show the solution, what it actually represents. The steady state solution will be just a minute, just 1 minute. Sorry for the interruption. Instead, they have actually represented it as a vector, how these two are actually related. If you just consider that here, pi 1, pi 2, pi 3 actually are same. So what happens? Pi naught will be 1 over this quantity. So if we write this is as a vector, then pi naught will be 1 over 2 plus twice u 1 minus u naught. Then pi 1 will be u1 into pi naught, actually is 2 plus 2 u1 minus u naught. And then this, and finally, pi c will be 1 minus u naught minus u1 divided by 2 plus 2 u naught and this one. So these two are identical. Instead of writing this one in this way, what the text teach, it actually brings this one out from the vector. And that's why for pi naught, it is 0. For all t's, that means from pi 1 to pi n, we'll have u1, u1, u1. And for pi c, we will have 1 minus sigma T1. Now, a generalized solution is given here. We have a specialized solution. We assume n equal to 3. That's why this quantity becomes 2. This book has actually generalized solution. So E1 will be multiplied by n minus 1. So that's why the generalized solution for this Markov chain, this one, if you consider these dots are here, a generalized solution will be there. But we actually, for the sake of solution, easier solution, what we did, n is equal to 3. And so we come up with this solution. So this is what is the steady state solution of the Markov chain that represent the CSMA CD transmission state, idle, transmitting, and collision. And from here, we can easily calculate the throughput. This throughput will be actually for all the T1 to Tn, actually successful transmissions are there. So we need to sum all this. That's why, since there are n slots, the probability is multiplied by n. And sorry, once again, sorry. And if we plot this one for a value of n is equal to 10, that means the transmission time is n times the collision detection times. And there are n stations. We use a 1 persistent with a collision avoidance mechanism, which eventually becomes the P persistent CSMA-CD. And what happens based on the input traffic? This line actually is for Aloha with a maximum throughput 18%. This dashed line is slotted Aloha with a maximum throughput, as we have already seen, 36%, 36.8 or 36.9 something. And the solid line represent the CSMA-CD, which actually approaches almost 1 as the load increases. From here, we can consider the successful probability, where NA is the probability that there is a frame in the network. That is, A is the probability that a single station is a frame. NA is the probability that any station, the total probability of a packet in the network. Then, then they calculated the delay, actually, average number of attempts per successful transmission. So how many collisions a frame will experience, a station will experience before it starts the transmission successfully. It is geometrically distributed with, actually, since it is the average number of attempts failure before a success, that's why the average will be 1 minus P by P, as we discussed in the class. Then, you have any questions or not? Before I move on to CSMA-CA, you have questions or not?
No,
No,
sir.
sir.
No question? Okay, very good. This is very silly, right? Very simple analysis, but CSMA-CA, as I already mentioned, only one difference is we do not have the collision detection mechanism. We will see 2 different versions of the CSMA-CA, and we'll understand that the assumptions in a model, how must it affect? So we will see, based on the assumption, how can we make a model very, very simple? How can we make a model very, very complex? Or how can we make a model very much realistic? Can anyone explain the CSMA-CA mechanism? Actually, what happens there in CSMA-CA? Especially, I want to actually know the collision avoidance part. Anyone? We need it. That's why before going there, let me explain it. What happens in collision avoidance, the channel time is divided into slots. This slot actually is a very small amount of time. The time actually we define as a slot depends on the transmitter or transceiver. This one actually is the time when a transceiver can switch its transmission states from transmitting to receiving or receiving to transmitting. So, and this amount of time is required for assessing the channel, whether it is actually free or not. So it is actually the time the station requires to first. It is in the receiving state and it checks that the channel is free. When it checks it channels is free, then actually if it has a frame, it actually starts the transmission. To start the transmission, what it requires, it requires to actually change the transceiver from the receiving mode to the transmitting mode. So we call it a slot. Now we also divide the channel time into other actually time period, one of which is SIFS. This one actually is IFS, and another one is DIFS. So let's start with the DIFS. Anyone knows what is the meaning of DIFS?
Yes. And
Actually, the CA or 802.11 has two different modes. One is DFS, another one is PFS. Here, DIFS is the, anyone is talking? Then I can hear. What is DIFS? It is distributed interframe space. Before a station actually start the transmission, the channel has to be free for this amount of time. And in between a data packet transmission and an acknowledgement packet transmission, there should be a time, we call it SIFS. So when a station actually completes the transmission of a data packet and it goes for, it waits for the acknowledgement, no other station actually start the transmission of their packet. That's why this gap SIFS is intentionally made smaller than the DIFS, because a station has to be sense the channel an amount of time DIFS before free before it can start a transmission. And once it actually find that this DIFS amount of time the channel is free, it guarantees that a new transmission will not actually collide with a successfully transmitted packet, which actually is waiting for an acknowledgement. As you already know, since transmitting and receiving are not simultaneously happen, a station actually after sending a packet waits for an acknowledgement. So to guarantee that an acknowledgement packet will not be actually interfered, the SIFS gap is there and the IFS gaps are there. This is one thing. Second thing is that if two or more stations are waiting simultaneously, then a collision is obvious. In CSMACD, they don't bother, because if a collision is there, the collision is detected almost within this amount of time and they can get back to the idle state. In CSMA-CA, since there is no way of actually collision detection, so stations now are more cautious in starting a transmission. What we have these slots after the DFs. A station actually randomly picks a number. The number actually we call the backup value. And it is actually uniformly distributed between 0 to some C window mean. We'll define more explicitly this one later. So a uniform random number in between 0 to C window mean is chosen by a station. We call it backup value. What it does, the station does, after the DIFS period, if the value of the C backup value is 3, then it has to wait 3 empty slots. So it picks the value 3. After 1 slots, it decrease the backup value by 1. Then another slot, it decrease the backup value 1. Then another slot, it decrease the backup value 1. So when the backup value becomes 0, the station transmits. Now, even though 2 or more stations are waiting simultaneously, they will choose different values, and probabilities are less that they will start their transmission simultaneously. That's how they avoid the collision. Now, if 2 stations are there, one is taking the backup value 3, another one is taking the backup value 5, what happens? The one which will reach the value 0 before that another station, the other one which has a smaller value of a smaller backup value 3 will actually reach the value 0 and start transmission. So as soon as the second station will actually find that in a slot that we will find that, for example, after the DIFS, the station actually after 3 slots, it finds that this station 1 is transmitting and this station 2 will find the channel busy. So it will freeze the backup operation. So here the backup operation will be freeze. And when this is freeze, the backup counter value that we call backup counter will be actually freeze to the value 2. And after the transmission, this So are we back?
Yes, sir.
Yes, sir.
Okay, sorry for the interruption. Somehow the IoT network actually has a so editor 11 is here. Now what will we do? The editor 11A, editor 11 can so the DCF distributed coordination function can be actually modeled in a very complex way, we'll see, or it can be modeled very simply like the CSMS setting. Let us first see how the CSMS CA can be modeled like the CSMS setting. We will directly jump into this space. It is okay. So same as the CSMS city, this part. Now, since during transmission, a station cannot actually detect the collision, a station cannot receive the signal. If a station has two transceivers, one for transmitting the signal, packet, another one for receiving the packet, then actually it is very simple. It will, the CSMS CD could be applied here, but the transceivers are expensive. Most of the cases, a station has a single transceiver. So even though a collision occurs, the stations keeps transmitting the frame, and after the completion of the frame, it goes back to the idle state. So the probability of transition is here, the solution is here, same, just you can find it. You can actually you can derive the system of linear equations and you can solve it. The solution is this one, and accordingly you can calculate the throughput like before. We will not here. We will not show it. Rather, we will show it the complex one where we will model the 802.11 DCF. Here, one thing that you have to notice is that the collision avoidance actually is not considered by this model. This model actually assumes that after an idle period, a station will transmit with a probability U1. A station will actually jump into a collision state with probability 1 minus U0 minus U1. But as I mentioned that a station, if this is the channel time, if it has a frame, say during this time it has the frame, so it has to wait for a period of time DIFS. During this DIFS period of time, the channel has to be free. Then it has to pick a random number. We call it the backup counter value, let's say B. And in each slot, the backup counter value is decreased by 1. If by this time another station starts the transmission, the backup counter value, actually B prime, is frozen here. Then it again, after the completion of the time, it again wait for a DIFS period of time and then start decreasing. And when the backup counter value somewhere reaches 0, the station starts the transmission. So all of these things are missing. Not only that one, setting the backup counter value is following a binary exponential backup. Can anyone tell what is this? This further actually avoids the collision, especially repeated collision. In binary exponential backup, when a station actually transmits or attempts to transmit a fresh frame, it sets the backup counter value B uniformly in between 0 to C window mean minus 1, more explicit. Previously, I just mentioned C window mean. Actually, it is C window mean minus 1 because the value is, if the C window mean is 32, then a random number is chosen in between 0 to 31. If a frame experiences a collision, then actually it goes us into the ith backup state. In case of the first retransmission, the backup value is chosen uniformly in between 0 to 2 into C window mean minus 1. For the second retransmission, the backup value is chosen uniformly, and I think you can recall this symbol actually tilde represents the distributed as. So uniform in between 0 to 1, this one is in between 0 to 4 into C window in that we will see now. The ith backup state, the backup value is chosen in between 0 to 2 to the power I into C window mean minus 1. So the collision avoidance in the binary exponential backup mechanism actually is each time a station experiences a collision, the backup window size is actually doubled. We start with the backup window size, say 32. Then after one collision, it becomes 32 times 2 becomes 64. That means from 0 to 63. Then after second collision, when it attempts secondary transmission, the backup window value is chosen 0 to 128. And in case of the ith retransmission, the backup value is chosen 2 to the power I into. So every time a collision occurs, backup window is chosen from a broader. The backup counter value is chosen from doubled backup value. Okay. Now, that model actually did not consider this one. But this one actually is directly from a paper written by an Italian. If I do not make, I will upload the paper here. So Bianchi. This is one very rare thing is that this is a single author paper actually as part of his PhD dissertation. This paper was published in IEEE Journal on Selected Areas in Communication, I think in the early 2001, 2. And one of the best paper I have ever read. So it models the CSMA-CA DCF mechanism. And unlike the other one that we actually got from the book, it models the DCF mechanism. Now in the DCF mechanism, two things that we need to consider is we have a backup counter value. After every successful transmission or after a collision, any station sets a backup counter value uniformly in between 0 to some maximum, the window size. And the window size depends, let's say this is the BT, a stochastic process. Let's say if there is no retransmission, if a station has a frame, it chooses a value in between 0 to 31. And when the value becomes 0, it just transmits. And there is no transmission, it goes for the next frame. Now, if we include the retransmissions, then what happens? You need to mention that in which state the station is currently in. By the time state, whether it is the first retransmission, second retransmission, third retransmission. Based on that, actually the backup window will be chosen. So we have another one, let's say backup stage. Another stochastic process. 0, 1, 2. A station can be allowed up to R transmissions. That means R minus 1 retransmission. In this model, there is one assumption. They actually did not discard, the Bianchi, actually the author, has not discarded a frame. Rather, when it reaches the maximum retransmission limit R, instead of dropping the frame, it keeps actually retransmitting the frame, but it does not actually increase the backup counter value, backup window size. So we have a two-dimensional stochastic process, BT and ST. And when we have this two-dimensional stochastic process, then another thing that we need to consider is that what is the, in case of a discrete time Markov chain, it is a two-dimensional DTMC. We need to mention this slot time. Here, one very clever assumption by the author is that a slot time is not fixed. A slot time can be of three types. One is the slot, real slot, where the channel remains idle. The second one is a successful transmission time, the packet transmission, and this one, and the DIFS, this one. During this period, a station, all other stations freeze their backup process. Another one actually is a collision time, which can be a little bit extended. Either way, we assume that it's a slot time. So when it is frozen, even though the length is much more than a normal slot, but we'll consider just one slot has been passed. In the calculation of the throughput, that actually is taken into account. Now, before we just finish the class, just let me introduce introduce the diagram. We will start with this one in the afternoon session. Just this diagram is a very simple one. If you focus on this part says the backup stage 0. That means a fresh frame is transmitted. A fresh frame is transmitted, and from here, a station actually randomly chooses a backup value in between 0 to C window -1. So what is the probability? A number in between 0 to W0 -1 will chosen. How many numbers are there? W0 numbers, C window mid. So any of the number is chosen is with probability 1 over W0. This is the case. And why this 1 minus P is multiplied here? A station comes to this point after every successful transmission. This one is backup state 0, this one is backup state I, this one is backup state M, and this is backup state 0. So at this point, when the backup value becomes 0, a station transmits. And with a probability P, a collision occurs. When a collision occurs, the station actually enters into the next backup stage. And what happens? In case of this one, W1 actually is 2 times W0. The backup window size actually is doubled. And one of the backup window value is randomly chosen with this. And this occurs with a probability P. Because a collision occurs probability P, and the station has to choose one of the slots from this backup stage. Or with the probability 1 minus P, a success occurs, the station again chooses a backup slot in between 0 to W0 -1. When again station actually after choosing, when a backup window value is chosen, then in every free source that I mentioned, if the station finds free slot, then it decreases the value to by -1. So 2 becomes 1 with the probability 1, 1 becomes 0 with the probability 1. And when the value reaches 0, the station transmits. So in short, for a frame, whether it's a fresh or it's a retransmitted, a backup window value is first chosen, which is 2 to the power I into W0. W0 is C window mean. And uniformly a backup value is chosen. Once the backup value is chosen, the station actually in each free slot, the station decreases the backup value by 1. When the backup value reaches 0, irrespective of the stage, it transmits. And it's after a successful transmission, it goes to here, and the backup counter value is reset to just W0. So I equal to 0, 2 to the power 0 equal to 1, it becomes this. And if a collision increases, the value of I is increased by 1, and the backup window size is doubled, and the random value is chosen, and the backup operation goes. So here we can have 32. In the second stage, we can have 64 state. And in case of M, according to the 82.11, there can be 1024 slots for actually backup slot values. Okay, we will see it in after the break. For now, we finish here. If you have any question, then we can do you have a class after this.
Yes, sir.
Okay, then actually I should not take your time. So we will have the second class at 1 p.m. inshallah. And another one, you need to submit the second part of the report. As I talked to one of your CRs yesterday, there will be single presentation during 27, 28, or 29. It is not necessary that all you have to assemble together, but you will come. The presentation, I'll be waiting in my room, hopefully. Okay, thank you very much. For now, we'll inshallah meet again at 1 p.m. Thank you very much.